So hello, I'm CU from Purdue University. It is my honor to be given the chance to come here to talk about our latest work called SymCerts on finding semantic problems in software code that does X509 certificate validation. So this is a joint work with Omar from the U of Iowa, Christina, who also happened to be the session chair from Northeastern, and then Du, Huangyi, as well as my two advisors, Aniket and Ninghui from Purdue. To begin with, X509 has long been used in TLS as a way of doing authentication and key distribution. It is worth noting that many times the confidentiality and integrity guarantee that TLS provides are kind of built on top of the ability of doing those too. The X509 PKI realizes the concept of so-called chain of trust. What it means is that given a chain of certificates from a server, a client is expected to verify the chain of certs and see whether he can extend the trust from a trusted root CA down to an intermediate CA cert, and then all the way down to the one of the server. Sounds easy enough, I guess. But from yesterday's talk, yesterday Yasmin told us in her talk on cryptographic API, I think none of the participants in her user study managed to implement certificate validation correctly. And also, we talked to some developers of TLS libraries, and some of them seem to have somewhat negative feelings towards the task of implementing support for X509. So it turns out that what makes it difficult is that apart from the cryptographic signatures on certificates, you have just so many other different things that you have to check. So for example, you will be given different names that are made of multiple attributes, and you are expected to match them up. And then you also have to do some daytime checking, which turns out to be also surprisingly difficult. And perhaps more importantly, you are given some optional but possibly critical extensions that you have to get processed correctly. Now, if an implementation is deviating from the specification, it can come in two different flavors. So for example, if an implementation turns out to be overly permissive, then you might be susceptible to different kinds of attacks. And if the implementation is overly restrictive, then you might lose service. We noticed that in recent years, there's a huge demand for internet-connected embedded systems, and because they have generally very limited amount of resources as well as processing power, developers have been making new TLS libraries for these platforms. Generally, these libraries would be written in C, and they are heavily optimized to kind of make them run better on resource-restricted platforms. And we noticed that there are multiple such libraries being released under the open source license. And perhaps because of their impeccable performance advantages over the traditional and perhaps heavier TLS libraries, we are seeing a new trend of app developers trying to take advantage of these small footprint libraries in their day-to-day app development, even on desktop platforms. Hence, the focus of our research is to expose noncompliance in X509 certificate verification in small footprint TLS libraries. And for that, we will take RFC 5280 as our main reference. The motivation for this paper is simple. Given small footprint, small code base, it should not be the case that the library is kind of compromising and sacrificing too much of security. And because TLS is such a critical part of our modern day security, it has been studied a lot. And when it comes to testing software implementation, I think black box fuzzing has been kind of the most prominent approach, where researchers try to look into the problem of protocol state-machine transition kind of problems, as well as a highly relevant paper that also got published at SMP 3 years ago, which also looked into the problem of X509 certificate validation. So the observation that we use into developing our approach is that given a universe of all the possible input certificate chains, a library essentially does one thing. It splits the universe into two possibly smaller universes, one that it accepts and one that it rejects. With that in mind, our white box approach goes like this. So for each of the library, we feed them input that we refer to as SymCert, and symbolically execute the portion of the code that is in charge of validating certificates. The purpose of that is to approximate the two universes and have them represented in logical formulas. Given the availability of multiple different open source implementations, we can do a differential testing by doing a pairwise cross-validation. So given two different implementations, if you can find such a certificate that one library would accept and one would reject, then you have a discrepancy that signifies problem. And because these approximations are in logical formulas, with the help of SMT software, you can do all these kind of automatically. Now, you might be thinking that this sounds too good to be true because symbolic execution is simply unscalable. Now, indeed, symbolic execution is cursed by the problem of path explosion, where, first of all, each conditional statement contributes to a multiplicative factor. And things get particularly bad when you have loops that are depending on symbolic values. So to make symbolic execution practical for our particular research problem, instead of making a whole certificate chain symbolic, we mix concrete values with symbolic values. Think about X509 certificates in DER encoding. Essentially, an encoded cert would be a tree of tag, length, and value triplets, where value can be further recursively defined by more TLV triplets. So the key idea here is to keep T and Ls to be concrete. And then for the leaf V nodes that correspond to certificate fields and extensions, you can make them symbolic. We also try to limit our scope for our analysis, and we also draw some more kind of domain-specific observations. So first of all, we don't try to comment on whether the implementations are doing correctly in terms of cryptography. And we also try to simplify the string matching, which I think the next talk in the session will give us a bit more insight on that. And finally, we break the original problem into smaller independent subproblems, where we essentially make different things symbolic at different times. With all that said, I think now would be a good time to show you some of our findings. We have a lot of findings, so I cannot go through all of them. I would encourage you to read our paper if you have the time. So we applied our approach into testing 9 implementations from 4 different families of TLS libraries that are actively being used and deployed on real IoT products, as well as on desktop app development. And we found a total number of 48 instances of noncompliance. And you might have noticed that I switched the template midway through. I am hoping that the red color would wake you up because I have something interesting to show you. To summarize our findings, we found numerous certificate fields and extensions not being checked, and some libraries would mishandle unrecognized critical extensions. And we also found incomplete implementation in some of the libraries. It looks like the developer wanted to add certain features, but perhaps due to release deadline, they didn't get to finish it completely. And then we also found incorrect interpretations of some semantic meanings of certain certificate fields and extensions, as well as the RFC itself. So the first piece of interesting new finding is that we found in multiple libraries, they are misinterpreting the 2-byte year of UTC time. So the RFC says for UTC time, the expected range of the year should be between 1950 to 2049. Unfortunately, for matrix SSL, they put the boundary at 95, effectively implementing a range between 1996 to 2095. This has a severe implication because certificates that got expired back in 1995 would be considered to expire in 2095, which reminds me of a certain famous sci-fi movie. A similar issue exists in Tropic SSL, but the mistake is actually different because they put the boundary at 89. And we also found that AXTRS has a similar problem, but it looks like the developer perhaps misread the RFC because it's only off by 1. However, the problem of having some boundary cases got shifted by 100 years would still be the same. A second highlight of our findings would be how sometimes libraries would opt for a lax comparison logic. Take this as an example. So on certificates, you can have this extended key usage extension, which mandates the purposes of a key that can be used for. and purposes are uniquely identified by object identifier. For example, server authentication would have this particular OID. Unfortunately, in both matrix SSL and wolf SSL, instead of trying to match the bytes exactly, they just take a summation of the encoded bytes and then try to match only the sum. So in this scheme, they take 71 to represent server authentication. Now this is problematic because OIDs are meant to be unique hierarchically, whereas the summation of bytes is not. And this is an example of implementations being overly permissive because some garbage OIDs would be considered to be meaningful. And it also presents a compatibility issue because some legitimate custom OIDs would be misrecognized if their sums happen to collide. And then we also found that in AXTLS, given subject names and issuer names with multiple attributes, they do not check country, state, and locality. Meaning that if you have a CA in the US, and hypothetically you have a CA of the same name in Australia, the two would be considered to match. And then we also found an ineffective sanity check in matrix SSL. So the function that I'm showing you here on the screen, its purpose is to perform some basic sanity check on input date strings. However, because of the if conditions are pretty much all of them unsatisfiable, it actually never rejects any strings due to an incorrect usage of the logical operator. For scientific curiosity, we also revisited some of the libraries that the previous fuzzing paper tested. Specifically, we have some new findings regarding these two libraries. First, in SymSerts, we noticed that there's a hidden coding mistake in the parsing code that parses certificate extensions. It turns out that this piece of code is a lot like a poor grad student. Both of them are missing a break. This is bad because the parser is incorrectly parsing certificate extensions, which means in the end you have some extensions mishandled. Our speculation here is that because this bug, given concrete test cases, doesn't seem to trigger an observable crash, perhaps it would have been hard for fuzzing to kind of catch this bug. Also in SymSerts, we found an overly restrictive time check. Recall that on certificates, the validity periods are meant to be inclusive. But we found a hidden coding mistake in the functions that does daytime checking. So if you look at the function names, they're showing correct intention. But if you look closer, the negation of greater than is less than or equal to, not less than. And because of that, SSL turns out to be overly restrictive, since they would be incorrectly rejecting some valid certs. Because this is a specific boundary case among a large number of possible values, perhaps it would be difficult for unguided fuzzing to perhaps hit this bug. One more discussion that we have is regarding the path length constraint in SymSerts and Polar SSL. Path length constraint is a part of the basic constraint extension. It is used by upper-level issuing CAs to restrict the length of a chain of certificate that you can construct from here on. Now, in the previous work, it has been reported that both SymSerts and Polar SSL are incorrectly rejecting certs regarding some corner cases of checking path length constraint. However, our findings suggest that both SymSSL and Polar SSL, along with Wolf SSL and Tropic SSL, they do not check path length constraint at all. So it cannot be the case that they are incorrectly rejecting certs due to this reason. Our speculation here would be perhaps the fuzz testing cases that they generated and used to serve as evidence for this particular claim also happen to contain multiple other problems that triggered a rejection in the libraries, hence resulting in a small inaccuracy in the claim. To summarize, X509 certificate validation, unfortunately, in all the tested libraries, they all somewhat deviate from RFC 50 to 80. And app developers might not know all these intricacies, all these details. So we propose a white box approach for exposing these non-compliance and semantic level kind of problems. And our experiments turned out to be quite fruitful. We found numerous problems, have them reported, and many of them got fixed. As a final takeaway, my advice to app developers would be to try to upgrade to newer versions of the TLS libraries that you are using. And I'm pretty sure I'm not the first one to say this. Many different people have been talking about this from different perspectives. So looking from the context of certificate validation, I think newer versions of TLS libraries, generally they have more bug fixes, better capability of handling complex inputs such as extensions, and generally they also have a more rigorous certificate validation logic. And with that, I'll end my talk, and I'll be more than happy to take questions from the audience. Thank you.
Hello, I'm Tomasz Kuchta from Qualcomm. Thank you for the talk. I have a question about the
Yes.
part where you compare the equivalence of constraints.
Yes.
I was wondering if I understand correctly, you would execute multiple implementations of certain library, of certain functionality, using symbolic execution.
Right.
But then to compare the equivalence, you would need to know sort of like which paths you compare in each of these libraries, right?
Right, so I think, so first of all, for each libraries, you essentially extracted path constraints that are kind of describing the two universes, accepting and rejecting. And as long as you keep the symbolic variables kind of the same name, then you can rather easily compare the two of them. So are you asking the problem of translating one path constraint from one library to another library?
Yes, exactly, yes.
Right, so that's kind of also the beauty of doing this at the symbolic level. So as long as you have the symbolic variables of the same name, then they are the same variable to a, say, SMT solver. So you don't really have this translation problem or ontological problem between different implementations, because the variables that we have, we gave the name to them. We are not looking at the code variables. We have variables that we named, which correspond to some certificate fields and extensions that we know of, and the two of them would match up.
Thank you very much.
Thank you. Yeah.
Hi, Philip Jovanovic, EPFL. Thank you for your talk. Can you elaborate a little bit more on how you selected the libraries for your analysis as you did? And for example, I missed like libraries like OpenSSL and so on.
Right, so that's a very good question. So we started looking at small implementations because they are useful and they are also easier to analyze, to be honest. And then due to obviously deadlines, we got our story and we kind of decided to do the small footprint libraries. And surprisingly, there are actually new libraries that are still being made. So I think 1 week before the open deadline, we found a new small footprint libraries that's being made, and people are actually using them. So it turns out to be quite okay for us to analyze these, and I think it's useful. And speaking of the bigger libraries, we are actually actively working on those, OpenSSL, NSS, and GNU TLS. And also some other possible implementations. Say X49 is also being used in perhaps IPsec, IKE, those kind of scenarios. We're also looking into that. So we are kind of working on follow-up work. Yeah, so
okay,
thanks. Thank you.
Hey, Juraj Smilovsky, University Bochum. I would like to ask, so what would need to be done to use this approach to verify TLS implementations, not only certificate parsing?
I think here we're looking at a different problem. So we are focusing on kind of the semantic level of verifying or validating certificates. It doesn't really have like a back and forth, different messages exchange. And it's also not like in TLS you have a somewhat or rather complicated actually state machine. And you don't also have a lot of kind of cipher suites and handshake messages to choose from. So I think in TLS that's one of the most difficult things, but here we don't really have that. So it's actually given the input what kind of scrutiny the library imposes on before deciding to accept it. So I think these two are quite different. Thank you. And can I steal 5 seconds? So I think I would also like to share with you the name of our paper. So I talked to some other researchers the other day, and they were saying that, oh, because you're mixing concrete values with symbolic values, isn't it concolic? And my answer to them was simple actually, because if I named my paper concert, it would be rather confusing and weird. So we kept the name SymCert. So thank you.